Last time we covered the Poincare breakoff-width theorem and some of its corollaries. There's a couple more things we're going to look at with our current discussion of universal algebras, though, developing algebras. The first thing we're going to look at today is extensions of derivations. And that is, of course, I believe, going to be extending a derivation from a group to its enveloping algebra, universal algebra, whatever you want to call it. Alright, so here is our lemma. We're going to pick a k-module V and its tensor algebra is going to be the T. Tensor algebra T. We're going to let U be an endomorphism of V, which means it is in the general linear algebra, of course. But let's write it as an endomorphism of V. Now, there exists a unique derivation of T which extends U, which means essentially the restriction of this derivation to V is just U. And this will happen to commute with the symmetry operators of T, which I believe are the ones that just permute the things that are being multiplied, you know. Now, here's our proof. We're going to let f be equal to n copies of V multiplied together. Then we have the mapping from a sequence of elements n long to, it's essentially we're going to have the tensor product, and we're going to be inserting this scaling factor into every possible spot, plus, and all the way to the scaling, this scalar multiple being in the last entry. This is a map of f, which is the product of n copies of V into the tensor of n copies of V. And this is, of course, multilinear. It's linear in every argument because, yeah, and remember this U, I guess it's not a scalar multiple, I misspoke, it is the image of this x1 under the endomorphism of V. And hence, I'm going to find an endomorphism, we call it UN, of the tensor product of n copies of V, such that UN of the tensor of a bunch of these is just the same as the image above, with this endomorphism acting on each entry in the tensor individually for all xi in V. Then the one-dimensional case of U is equal to just U itself. So we're going to let V be the endomorphism of the K module of T which coincides with UN on each T to the n, which is the tensor of n elements of V. And is, of course, 0 on tensor 0, which is our copy of K. Now, this is our derivation in question. But how do we know that this map V is a derivation? I mean, the idea here behind this map V is pretty clear. We just need to make sure it satisfies our definition. And keep in mind the product, not the Lie bracket, but just the algebra product on a tensor algebra is just the tensor product. So we need to show that V splits across a tensor product as we would want. You see that V of the tensor of, we'll go say the tensor of elements x1 through xn. And this is going to be tensored with, of course, a tensor product from elements y1 to yp. This is going to be equal to the sum from 1 to n of essentially, we're going to have x1 tensor all the way up until x to the I minus 1, and then x to the I, where that lands, is going to be put through this u. And then we continue on with normal all the way back up to xn, and then we start on the y's, and once again everything is normal up until yp. And then we also get how this acts on the elements on the other side of the tensor, which is going to look much the same. Tensor through xn, tensor y1, tensor through yi. I guess we should call this j, not that I don't think it'll matter. And keep tensoring up until y of p. And we see what is this thing actually? This is on the left side. This is the tensor of V. This is V acting on the left element of our tensor product through xn tensor all of these y's plus, and then it's going to be on the other side as we'd want. And so this is in fact a derivation. Running out of space here, but you get the idea. And I mean, the condition with the symmetry operator is pretty straightforward. And so we'll just call it there for that proposition. So now we know how to send a derivation from just any module to its tensor algebra. And from that, we want to look at how it acts on the enveloping algebra. That's going to give us our next proposition. We're going to let G be a Lie algebra. With enveloping algebra U. U and a canonical map sigma from G into U, and we have capital D be a derivation of G. And there's two consequences we get. First off, we can find a unique derivation du of U such that taking our base derivation on G and then sending that into U is the same thing as taking the element into U directly and then doing this new derivation. And keep in mind, as I said before, we can identify G with a submodule of U. So it's essentially, once again, saying that the restriction of du to G is equal to our original D under that identification. And our second condition is that this du will actually leave un stable and the set un u super n of images of in U of the homogeneous symmetric tensors of order n over G. Now, There are, in fact, two mark conditions, which were on a different page. So let's take a look at those as well. See, a du commutes with the principal anti-automorphism of U. Condition D, that if D is an inner derivation, it says it's the inner derivation of G defined by an element X, which I'll just write as if D is the adjoint in G of some element X. Then we get that du is, of course, the adjoint in U of the image of X inside of U. Alrighty. So how do we know all of this? So we're going to let dt be the extension of D to the tensor algebra of G, which is T. And we saw the proof that this exists and is unique in our previous proposition. Now, as we've seen before, the two-sided ideal J of T, which is generated by, as we saw before, X tensor Y minus Y tensor X minus their Lie bracket is stable under this dt. How do we know? Well, dt of X tensor Y minus Y tensor X minus the bracket of X and Y. Well, we know that by linearity this is going to act on each component individually. And we also know that it's going to split over both the tensors and the Lie bracket based on what we saw in the previous proposition, which means this is the derivation of X tensor Y. Alright, right on two lines like they have. So X tensor the derivation of Y minus Y tensor the derivation of X minus derivation of Y tensor X minus the bracket of dx and Y minus X dy. Notice that this top line is in J substituting X with dx, and likewise this bottom you substitute Y with dy. And so we see that J is stable under dt. So by quotient, under passing to the quotient, dt defines a derivation du of u. So essentially what we showed up here, because keep in mind we're going to get u is the quotient of t by j, and we have now that our dt acts across each j, each equivalence class generated by j. So we can just take the quotient of this map with j. And this is, of course, going to meet our condition that it is the equivalent of d across the injection sigma. And we see that du is unique since we have both this one and the image of G, as we saw before, generates RU, and we know how derivation is going to act on each of these. And that now gives us B, so we've got A and B done. We can go with C, and we're going to call this principal anti-automorphism A. So, if we have a collection of n elements in G, then we have that du of the anti-automorphism of the product of the image of each of these xi and u keep in mind this is a product of n elements, and so this is going to be sent to -1 to the n times our standard product of u, but this time in the opposite order. Which is going to be, as we saw before, the sum I guess we'll bring this multiplicative term out, this scalar in front, and it's going to be the sum of x to the n, and then the derivation in u of this sigma, then back to normal all the way back up to x sigma 1. And we know that we saw before that du of sigma is just sigma of d. And so this whole thing is just, once again, the anti-automorphism of this product done back in the right order of sigma dxi through sigma xn, which is the composition of A with du of the product in the normal order of the sigma xi's. And this is our original formulation with A and du swapped. Now, just left to show that if D is an inner automorphism, du is the inner automorphism that you would expect. So we're going to let X be in G, and we're going to define an inner derivation delta of X, of Y defined through X as sigma X Y minus Y sigma X. So this, I believe, is the adjoint representation of sigma of X. This can be an inner derivation of U. Then for each x prime in G, we have that the composition of delta of sigma acting on x prime is plugging that into our formula above minus sigma of x prime sigma x, which, given that sigma is a morphism, we can turn this back into the Lie bracket. And this is just the composition of sigma. That's x prime, sorry, not y. And which itself is just the adjoint representation of x acting on x prime. And so the adjoint of x in U of sigma composed with sigma is sigma on the adjoint representation of x in G. Alright, should I write this part down? In the case of a commutative Lie algebra, when the Lie algebra is commutative, every endomorphism, we call it U, of a K-module can be extended uniquely to a derivation of the module's symmetric algebra. This is done through the quotient from the derivation of the tensor algebra which extends U. I guess of would be a better term than from in this case. So here's another thing. Going to let G be a Lie algebra over K with a derivation D. And T is its tensor algebra, S is its symmetric algebra, U is its universal enveloping algebra, and G is going to be its graded algebra. We're going to extend D to T, D and D to S separately. I'm going to let du, of course, be extension to U, such that sigma acting on D, this canonical injection of G into U, be the derivation in U of acting on sigma. This will, of course, as we saw, this will leave each UN stable. Thus, we see that du defines by quotient a derivation dg on G and since we got both du and ds, these are derived from our dt by quotient. We have from our old diagram, which they refused to reprint, and I'm not going to go back to, that d and g can be derived from ds by the homomorphism we saw earlier from G to S. Now, if the characteristic of K is 0, the isomorphisms map so if character of K is 0, we can map restrictions of dt ds, du, and dg into s prime n, sn, un, and gn. Hence the canonical isomorphism, which I believe was the Poincare-Birkhoff-Witt theorem, which is a canonical isomorphism from the symmetric algebra into the universal algebra, maps derivation of s into the derivation of u, since all of the substructures map as we'd want. And we actually have one more topic before we finish this chapter, which we will have time to cover right now. And that topic is once again extensions of the base ring. I have no idea how to capitalize these titles. So same setup, let G be a Lie algebra over K. With a tensor algebra of T. And two-sided ideal J of generated by x tensor y minus y tensor x minus the bracket of x and y, such that U is T over J. Going to let K1 be a commutative ring. Ring is not an abbreviation, that is the full word, with a unit element and an injective homomorphism sigma mapping K into K1. Then the tensor algebra of the extension of our Lie algebra G to K1 is canonically identified with taking the extension of the tensor algebra. We're going to let J prime be the two-sided ideal of tensor K1 generated as you'd expect. Let's write expected here. That is x prime tensor y prime minus y prime tensor x prime minus the bracket of x prime and y prime for x prime and y prime in G extended to K1. And it's pretty clear that the canonical image of J, the extension of J in the extension of a tensor is contained in this ideal J prime. And to see that they are equal, we will show that for all x prime and y prime inside of the extension of G, x prime tensor y prime minus y prime tensor x prime minus the bracket x prime and y prime lies in this image. Alright. So we're going to write x prime as the sum of some xi with some lambda I, and y prime as the sum of some yj with some mu j. And keep in mind how you extend bases. These x and y are going to be in G, and these lambda and mu are going to be in our new extended ring. And so we get that x prime tensor y prime minus y prime tensor x prime minus the bracket of x prime and y prime is just the sum over both I and j of xi tensor yj minus yj tensor xi minus the bracket of xi and yj. And then we of course are going to get our leftover elements of lambda I and mu j, their product. And this proves our assertion, and we see that the extension that u of k1, which is t over j, k1 is canonically identified with the extension of t over j prime. And we see that the enveloping algebra of the extension of our Lie algebra, G, is canonically identified with this UK1 and the canonical mapping of our GK1 into its enveloping algebra is identified with the canonical mapping of G into U tensor just 1. And that is the end of this chapter. There is another chapter on representations coming up next, But I think I'm going to mention here before that, we're going to go over the contents of the universal algebra again, but this time from a different source. So hopefully we should be able to get a bit more insight, a bit more diverse of a look at this from a second source. So there's going to be a couple more videos going over this from a different perspective, different text, very different approach. Hopefully that is still going to be interesting. Yeah.